walk through the code that I want you to write for displaying the data to the 7-segment displays. But let me put this into some context to make sure we understand exactly what we're trying to accomplish. So remember, what we're trying to do is we're trying to control what shows up on the display. So here's display 3, display 2, display 1, display 0, and we're pressing these buttons. All right, and what happens with the buttons is it enables each of these segments to use the data lines that gets from the switches to the display. So in other words, if I want to display the data, all right, so we have data showing up on these 4 switches that represent digit 3. Think of this as BC, binary coded decimal, BCD. Okay, so those 4 switches, when I press this button, this display is enabled, so I can use those shared data lines and display that digit. All right, so just to show you the schematic, remember for the FPGA board, you only have the 7-segment lines going to each of, they're shared between all the 4 displays. And so the variable that we use with the constraint files on this is the seg 6 down to 0, so 7 bits. There's also something for the decimal points for each of the displays. We're not going to hook those up. But then you control which one turns on with this anode signal. All right, so if you want to turn on display 3, then you make anode bit 3 equal to a 0, and the rest of these need to be 1s. Okay, so you cycle through that way. The other thing we have going on with the boards is we have these push button switches that I showed you in the previous diagram. All right, so you can only press one of these at a time, all right? And so that's how we're going to cycle through our display. So that's the context of what we're trying to do. All right, in our top level display, the top level design for Lab 6, I'm showing here that you have the switch configurations going to this display logic that we're going to be writing. And you take the 4 different inputs, all right, and you have to send those 4 outputs, send one of these, depending on which button is selected, to the output, and that output gets sent to the 7-segment decoder. We talked about that in a different video, and that shows up on the display. And we enable the displays by going through the button sequence. So if I press button low will be high, these other 4 bits will be low, everything gets inverted. Remember, it's low true for the anode. All right, so that's the setup of how it works. All right, but we're trying to learn Verilog as we go. The point is not necessarily, the project itself. The project is a vehicle for learning Verilog. So I wanted to talk a little bit about how the workflow goes whenever you try to develop something complicated. All right, so I tend to work, throughout my career, I've worked up here in the algorithm side, where we're looking at different communication algorithms or different algorithms to detect signals in the midst of noise, and to do mission planning and those kind of things. So up here, my main tool is MATLAB, but from there, if you come up with a nice algorithm and you want to implement this into hardware, sometimes you need to do that because the algorithm won't run fast enough, or you can't deploy it until you put it into practice in the hardware. So that shows up in things like cell phones. Like you have a cell phone algorithm that won't run fast enough unless you implement that into hardware. Right? So it turns out direct synthesis to hardware is easier as you move down this chain. So in other words, Verilog, I've never seen Verilog used at the transistor level, but I read that it can. All right, but let's say we decide to describe something in Verilog in terms of gates. Well, you can easily implement that. That's set up. It shows what all the connections should be. All right, and even at the level we've been working at, which is this register transfer level, some people call this the data flow level. It's easier to do hardware at these 3 levels. But then when you move into behavioral, you're trying to describe what happens with the circuit. And it turns out Verilog and VHDL, their origins were for simulation. Okay, we're going to simulate what hardware does so that we can make sure that it works before we get down to designing what it should actually be to implement, the logic that we're coming up with. All right. Well, along the way, people thought, well, wouldn't it be great if we could hop off right at the behavioral level and go straight to hardware? Well, you can in certain cases, and the cases we're going to be doing today, certainly the Vivado tool is able to synthesize the hardware. I always read about, oh, we're going to be able to go from MATLAB straight to code or straight to a fixed point code that runs real fast on a processor. All those things are possible. It's just more difficult as you live at higher levels of abstraction. Okay, so that's my take on it. Okay, at this point, I'm going to write Verilog code to describe this display module, and I'm going to do it in 3 different ways to help you learn Verilog. Okay, so here's the display module, and so you can see there's inputs defined, x0, x1, x2, x3, and an output y, and then we have also a 3-bit select line for the inputs, with the distinction being that these are never all on at the same, there's never more than one on at a given moment. They can none of them could be on, but there's only one at a time that would be on. So that lets us select different data lines to go to the output y. All right, so the first thing I'm going to do is use a data flow type of description. That's what we've been doing mainly in our class. We did a little, we did this behavioral description for the 7-segment display, but so far we've been focusing on Verilog descriptions that use assigned statements, basically. All right, so, but for all modules, you get set up by defining the inputs and the outputs. All right, so I'm going to call this data flow. And I've got a test bench already written for all these, and we're going to go through that in a second. But you ask yourself, how do I get started? You get started by putting in the inputs and the outputs. All right, so I'm going to have inputs, and they're 4-bit inputs in this case. So 3 down to 0. I have x0, x1, x2, x3. And also I notice that the select line is also 3 bits. Just nudge this over a little bit. So those are the inputs. If you're wondering, when do you use commas, when do you use semicolons, this is between parentheses. Think of it like a function call in MATLAB. You separate the arguments with commas. All right, and so you wouldn't use semicolons within the arguments of MATLAB. You don't use it in Verilog either. Okay, so then we have an output, and it's also 4-bit, right? And so that would be y, right? And just like in MATLAB, you don't have a closing comma in a function call, so you don't have a closing comma here. All right, so the next thing I'm thinking of is I want to use an assignment statement, and this looks a lot like a multiplexer. We did an assignment statement with a multiplexer in class. So what immediately comes to my mind is a multiplexer, but it's not trivial to do this one. All right, so let's take a look. Nudge this to the side where we can see it. This is the diagram I've written. So we talked about a conditional assignment statement essentially being a multiplexer. And so we talked about also how a multiplexer can be written in hardware with AND gates and OR gates. And so let's think how that would work. All right, a multiplexer, let's just take these one at a time. If S0 is a 1, then X0 goes out to the output. If S0 is a 0, then this input goes to the output. So where are we? If S0 is a 1, then I know the rest of these are going to be zeros. All right. So if S0 is a 1, X0 goes to W0, but then the 0 line is selected the rest of the way out. And so x0 would flow all the way out to y. All right. Conversely, if s1 is a 1, all right, if s1 is a 1, s0 would be a 0. Then I'd be looking at, is it w0 or x1? If s1 is a 1, x1 would go to the w1 wire. And then the rest of these would be 0 if s1 is a 1. And so that would flow it out to the output y. So that's how that would work. So from there, it's like we've done in class or in lab. We look at, here's the assignment, W0, then the conditional operator is implements this multiplexer. Okay, so let me put that statement in. I'm going to just cut it and paste it so I don't have to do all the typing. All right, so I cut and paste this. This is my first assignment. I got one extra assign here. Okay, so select is the test variable, then I put the question mark, then I put x0 is what happens if select 0 is a 1. The alternate condition is what happens if it's a 0. All right, so then I can do the same thing with wire 2. And so this is the result I get. Oh, notice I started using wires. If I'm going to use wires, I need to declare wires. All right, so Verilog will know what widths to use. Now, if you think about it, these are all 4-bit wires. So I need that statement there as well. And let me just copy the rest of these down. You can think about what they would be. Pause the video, try to fill in the next 2 assignment statements. There's one for W2, there's one for Y. All right, so pause the video and try to come up with those. All right, so what you would have gotten is these are the statements that would implement the rest of the diagram. All right, so from there, that finishes the data flow module. I need to close that with an in module. And we're done with this particular implementation. Is a behavior model, and we have the same starting point. We need to define the inputs and the outputs, so I'm just going to copy this and have a different name for the module. We're going to call this behave 1. All right, now it's going to be a behavior model, and we're going to use an always statement. All right, or an always block. All right, and because I'm using an always block, this needs to be a register. All right, so I have this as a starting point, and then when I do my always block, I need a sensitivity list, and here's the shorthand notation that says every variable that appears in this block is on the sensitivity list. We'll talk more about sensitivity lists as they become more relevant. They'll become more relevant when we do sequential digital circuits. Right now we're on combinational digital circuits. It's hard to know what a combinational digital circuit is unless you know the alternative. So, we'll get there. All right. When you have an always block, you need to put that between some begins and some end, a begin and an end. And then we need to start writing the Verilog code. Right, so one natural thing that you might think of is if statements. There are if statements in Verilog, and so let me write down the first one and we'll talk about it. I'm just cut and paste so it saves on typing time. All right, so if, all right, and then the format is I have the statement that I'm looking at. So I'm wondering, is this statement true? And because it's a logical statement, I need the double equal sign. All right, so if that's true, all right, then I make the assignment y equals x3. Okay, and then from here I have the else if conditions. I'm going to paste them all to save on typing. So let's examine those, all I'm doing is looking at the other cases. Else if select 2 is equal to 1, then we assign y to y2. If select 1 is equal to 1, we assign y to x1, and so forth and so on. That ends our module. Okay. So there's the module for one type of behavioral description. Show you an alternate way. There's many ways to do things. And so here's a different type of behavioral description. And we'll call this B-have-to. And everything has the same inputs and outputs because it's the same module. All right, so let me just cut and paste that. Again, because we're going to use a behavioral description, we need a registered output. All right, so that's one of the rules for an always block. All right, so from here, what I want to do is set up the always block. I have a sensitivity list, so the sensitivity list is everything. So I put @ to show that everything's on the sensitivity list. All right, next what I'm going to do is a case statement like we did with the 7-segment display. So I'm just going to paste that in, and because the case statement has its own begin and end, I don't need a begin end block within the always. All right. So normally if I had multiple statements in an always block, I would need a begin and an end. All right, but this is good enough. All right, and this actually closes this module. All right, so let's walk through it. It's like the 7-segment display. With a case statement, you look at the variable under consideration. So the select line is the variable under consideration. So when select has this bit pattern, we set y equals to x0, and so forth and so on, all the bit patterns that we talked about. The extra thing I have here is a default condition. All right, it's good to always specify a default condition because it helps with the hardware synthesis. All right, and so because I have 4 bits, there's 2 to the 4th combinations, and I'm only specifying 4 of them. All right, this default case takes care of anything that might happen to come up, or it helps the synthesis tool figure out what to do with the extra cases when it synthesizes the hardware. All right, so that ends that description of a second type of behavioral description of the same display module. It has the same functionality. All right, so next up, we're going to talk about the test bench for these 3 versions of the same module. Verilog descriptions of the display module for Lab 6 in 3 different ways. Okay, and these should, of course, give us the same result. All right, so I wanted to set up a test bench for this, and you're going to need to set up a test bench for Lab 6 for this module, and so this walks you through, the solution for that. All right, so how do you set up a test bench? Well, remember, the questions you ask yourself are, do you need inputs and outputs? Because it's a test bench, you do not. Okay, then how do I control the inputs to do the test on the module that I'm trying to test? Well, you have to set up registers to control those inputs. So we have registers set up for x0, x1, x2, x3, and select. All right, then outputs can be assigned to wires. You're driving the wires with the modules. All right, and so we do that. Then the next step is you're testing something, you need to instantiate that something. Now we're testing 3 different versions of the same module. All right, so I instantiate all 3 of those. These need different names. Okay, I've noticed people forgetting to put a name, and they'll have an instantiation that looks like that. That throws a syntax error. You don't actually have to have a label, but you need at least a space. And I think it's a good idea to put a label in there just so that you're consistent. Okay, then the next thing we talked about is you need an initial block because we're running something for the first time. So initial blocks are used for simulation. All right, that'd be a good multiple choice question. All right, so our initial block is going to have more than one line, so we encase or encapsulate that between a begin and an end. All right, and then I'm using EDA Playground just because I like how quick and easy that is. I need to set up a monitor so I can look at the variable changes, and this is how I have that set up. I don't know if we've walked through this very carefully before, but I have x0, x1, x2, and x3. This is just formatting stuff here, just like you would do in MATLAB or in C. And then the %h tells me what format I want that variable to be shown in. So I have a %h for hex. And the very first argument in my list is x0. So x0 would be given in hex, right? And so forth and so on. I put the select line here in bits because that's it's the bit pattern we're trying to detect when we're working with this display module. All right, so from there, I need to set up some inputs, and then basically what I'm looking at is flipping through the select lines for this data. All right, so that's a good first test for seeing if your display module works. And that's the level that I need for this project. This would be good enough. All right. So you put some data in. You should put different data so you'll know that so you can distinguish between the different outputs to see if it's working right. Okay. So at this point, I'm ready to run this. Remember, I have 3 different modules doing the same thing. I have outputs y0, y1, and y2. All right, I'm reporting my answers in hex. So what I'm expecting is, 10 decimal in hex is an A. So I want to see A, B, C, and D on the outputs when I run this. All right, this is what I'm getting. X0 is assigned to A, X1 is assigned to B, X2 is assigned to C, and X3 is assigned to D. When I have a select line, 0, 0, 0, 1, the Y is an A. All right, and it's consistent across all 3 module descriptions. So, this shows you that it's doing what it's supposed to do. When select line is 0, 0, 1, 0, I get B on the Y line, and so forth, C and D. All right, so hopefully this helps you with your Lab 6 project.